So let's look at this, boundary layer equations. So in the previous set of notes, we found the five-year average compressible continuity, which is mass conservation, momentum, and energy equations. And now we want to say, well, what happens if we restrict our flow to being turbulent or laminar or compressible or incompressible near a wall? It could be external flow, internal flow, it doesn't matter. So we're going to try and formulate the boundary layer equations and approximate them by observing some physical trends in turbulent boundary layers. And then we'll try and recover the mean kinetic energy and Reynolds stress equations, which are of K and Reynolds stress for boundary layer flows. So that's our objectives. And as you know, the Navier-Stokes equations for viscous compressible flows are going to represent the flow field, right? The velocities, pressures, temperatures, densities, enthalpies, etc. So that's our assumption. So you know it's a continuum. For, say, incompressible laminar flows, the problem is way simpler, right? Because we won't have any of these density fluctuations. So that would mean if it's laminar and incompressible, it makes life a lot easier. Is, of course, rho can be a constant, and if it's steady, we get rid of our time derivatives, which is good too. But the problem is it's still a hard problem to solve because we have multiple linked PDEs, and there's no wonderful solution for this particular case except for by Boussinesq. And in the third computer project, we'll basically find that solution. And I hear that this semester our undergraduate aerodynamics students are actually solving the Boussinesq equation in class numerically, and that's a third order ODE that can just be integrated from the wall to the edge of the boundary layer. What's good if you make the boundary layer approximations is that all our equations can be reduced to simpler forms, which is wonderful, and part of the reason why boundary layer theory is so popular. We might say that the momentum equation is expressing a balance between the inertial forces, the pressure forces, and the viscous forces. And that formulates equations, of course, where we neglected body forces. And one simplification might be is when we take some relative magnitude to these forces in comparison with others to try and do order of magnitude analysis to form the equations. And an example of that in boundary layer theory might be when some particular viscous forces or even components of that stress tensor are negligible with respect to the inertial and pressure forces. For example, in boundary layer theory, we might find that, say, partial P, partial Y is about 0 for incompressible flows, but for turbulent compressible flows that are high Mach number, partial P, partial Y is definitely not going to be 0 through the boundary layer. So a lot of these things are just drawn from experimental measurement and mathematical analysis to arrive at the final compressible turbulent boundary layer equations. Okay, so let's look at our equations of motion again. So if you go back, way back to equation 2.50 and our energy equation, which are maybe 2.53, we might write equation 286 and 287. And you'll recognize this as what? This is sort of like a Euler equation. And this is our energy equation. And you'll notice there's no viscous forces, so it's basically a set of Euler equations with first law of thermodynamics. Our continuity equation in that case is the same, which is 249. You'll see we have density in our spatial gradient. So once again, so we have 286 to 288 are base equations. You can use equation 288, I believe, to change 286 and 287. So 286 will become 289, 288 will become 290 using our continuity equation. So that allows us to pull out using this form here, the second term of the continuity equation, and modify the equation so we don't have density in the left-hand side of, say, 286. And it just makes it a little bit easier to work with sometimes. Now we want to say, well, we want to try and simplify these equations, 289, 290, and 288, to when a flow is moving past a solid body at high Reynolds number. So what does that mean? What are the observations? You might say that there's a very narrow region close to the surface in which the fluid velocity and temperature and enthalpy deviate considerably from their values far from the surface. So that's the first observation. And you know that because that's sort of the basis of boundary layer theory, which people learned previously. If you draw that, you have a surface. That's the surface, and there's some flow, u infinity. And very, very close to the surface, there's some turbulent motion. And that's not drawing the scale. This little area here, which would be the boundary layer thickness, is extremely small. So very near the wall, we have large turbulent fluctuations. And in that narrow region, you might say that your gradients of flow variables dominate. And the velocity gradients might be so large that even if the viscosity is small, the viscous forces may be orders of magnitude larger than the inertial forces. Right, dominate, even if mu is less than 1. It's on the order of epsilon, maybe a very small value. Like 1 times 10 to the negative fifth is a typical value of viscosity. So these viscous terms in the equation of motion, which we haven't written in this set back in the original Navier-Stokes equations, are dominating all the other terms very, very close to the wall. As you come away from the wall, the inertial terms and the viscous terms are in balance. And when you're far away from the wall, the inertial terms are huge and the viscous terms are very, very small. The viscosity, of course, could be seen as a constant or a weakly dependent on temperature. So this is an observation. And what are these things called where these properties of the flow happen? That's what we call the boundary layer region, and is indeed the layer affected by the fluid called the boundary layer, right there. And as you know, maybe you've heard in previous classes that this is basically the physical arguments put out in the 1904 paper by Prandtl, and that's in German. You would think I'm a native German speaker because I'm like 98% German, my dad's German, and here we are. So I have the paper, but I can't read it. Are there any native German speakers in the room? Or maybe secondhand? None? Okay. So this is why I think on the class website I've posted a history and effect of the Prandtl boundary layer theory. And if you look around, there's actually a book called Boundary Layer Theory by Schlichting, and that was one of Prandtl's students. So if you see that in the store, grab it, because it's probably one of the most valuable fluid mechanics books that I think exists. It's a lifelong work of Schlichting. Boundary layer theory. I guess I can bring it to the next class and pass it around so you can see my copy. Okay. A few notes by Prandtl. He noted that the gradients perpendicular to the surface are much larger than gradients parallel to the surface. So very, very close to the surface. You would think that terms like partial u, partial y are going to be huge, and partial u, partial x would be very, very small. And indeed, measurements show this. The growth and change of turbulent kinetic energy, like k, partial x, is very, very, very small in a fully developed turbulent boundary layer relative to, say, partial k, partial y, which is how turbulent kinetic energy changes as you're going away from the wall. So those are just two examples of this important observation. And in Prandtl's theory, which is basically still, kind of canon boundary layer theory today, there's two regions of these flows. There's the large region, right, which is sort of the inviscid flow away from the wall. And of course, there's the boundary region, as he put it. Very close to the wall. And this boundary region, that would be governed by the boundary layer, which I'll just write BL equations. All right. So he tried to divide the problem. It's the same set of equations. Viscosity does exist everywhere, but out in that inviscid, and it's not really inviscid, but it's like more of like a potential flow. Away from the wall, away from the turbulent fluctuations, you could just solve the potential flow equations. And they could be somehow matched with a simpler set of equations that we might have hope of actually solving within the boundary layer. And he divided that into two sets. There's laminar boundary layers and turbulent boundary layers. And we'll kind of look at the equations for both. And you can make additional assumptions like steady, incompressible, etc. So you can certainly have a hypersonic laminar boundary layer. And that exists on basically every hypersonic vehicle near the leading edge. So that's surprising to some people that you can have such high Reynolds numbers in laminar flow. So we want to try and derive those boundary layer equations and talk about their physics so that we can attack the problem and actually close turbulence models. And once we close turbulence models based on those boundary layer equations, we actually try and apply them to all kinds of different flows. The boundary layer flow is so important, of course, because it happens in basically all external aerodynamic flows, which is really important in aerospace engineering. So first, we're going to do focus on two-dimensional unsteady compressible turbulent flow. And like I mentioned, there's a potential or inviscid flow outside the boundary layer. So if I draw that, there'll be a wall, and then there'll be a boundary layer, which is some relative thickness delta, which is turbulent. I'll just draw all kinds of weird turbulent structures. And out here is this inviscid or potential flow. And they call it potential flow because, of course, they assume that it has a solution dependent on one variable, which is like a potential function phi, or like phi, and maybe some streamlined psi. And that can be done in 2 dimensions usually, and there's actually 3-dimensional potential flow theory that was developed by Qian, the famous hypersonic researcher. There's actually some NASA publications he wrote which outline that, but very few people actually know about that method and equations, which is unfortunate, but I just want you to know it's there. So out here in this potential flow area, this is all one fluid domain, and this line is just sort of denoted as like the edge where the velocity fluctuations are approximately equal to u infinity, which is like the mean velocity outside this turbulent boundary layer. Has everybody seen boundary layer theory in some capacity, I assume? Yeah, so some of this is kind of review, but I just really want to like emphasize like the thinking of the people who created this and why these equations came to be. So stop me if some of these concepts aren't clear, please. Now, so that's what's happening outside, and that's actually what we teach, like, entry-level aerodynamics students, is how to solve potential flow. And that's wonderful because you get rid of the viscous term. But then you kind of lose insight in all the laminar or turbulent boundary layer itself. So what happens in this tiny, tiny little layer right? So your whole fluid domain is huge around the aircraft, and very near the aircraft skin, you have this turbulent boundary layer. And at least, it has to have at least two velocity components, u and v. So u would be in the x direction, and v would be in the y direction, if this is x and y. And it might also depend on time, if it's an unsteady flow. And of course, all turbulent flows are unsteady. That's why we do statistical approaches. So x is usually the distance measured downstream on the surface from some point, and y is the distance from the wall, which is great. And just because our coordinate system and, say, u bar and v bar are non-zero, that might mean that w bar is 0 if we do an averaging technique, that there's no velocity in the cross-stream direction. But what about turbulent fluctuations? Even if we have this nice flow over a flat surface and it's turbulent, we would expect u prime, v prime, and w prime not to be 0. So you see the turbulence is 3D. And as we noted when we were talking about sort of physics of general turbulent observations in the introduction, you won't have vortex stretching in your turbulent flow if you say it's truly two-dimensional. So we might have a two-dimensional coherent system, but we need to let fluctuations go into the board, so to speak. Another thing, if it's compressible, we're going to have some sort of energy. It might be total enthalpy, and h is a function of x, y, and t, time. So making these assumptions and applying them to the equations I showed at the beginning of this chapter, we're going to have continuity again, and this is again with Favre averaging. Same definitions, right? So tilde is mass, and a bar is Reynolds, right? That's time averaging. And so we have our continuity equation, and you'll see now I've dropped the indices. So I'm going to just write out the whole equation like I've done in 291. So I have partial rho bar partial t, partial x partial rho bar u tilde, plus partial y rho bar v tilde is 0. No indices. So I've dropped the third component because w tilde w bar is 0 into the bar. I can use the same strategy in 2 dimensions to write out my momentum equation in 2 parts. There's no z. It's just zeroed out because I'm not tracking the w tilde component, right? So all those terms would drop out and the equation's not useful. So now I have equation 292 and 293. And then I have a total enthalpy equation. And I'm going to track mass weighted total enthalpy. That's nice. And we have a few other things here. Let me come down. I define my stresses, right? So before I had them in index notation. Well, now I just have tau xx, tau yy, and off-diagonal components tau xy. So remember, this is usually tau ij bar, and we would go from 1 to 3, but we're only in 2 dimensions because we only care about x and y coordinates. And so this would be I equals 1 to 2, and j equals 1 to 2. Those are expanded out, and that's why we're just replacing 1 with x and 2 with y. So we only have 3 components of the stress tensor, right? So how many are there total? Well, there's 2 by 2. So there's 4 elements in that stress tensor. And since it's symmetric, I only have to write 3. And that's why I write tau xy equals tau yx. So that's greatly reduced the problem already just by going from 3 directions to 2. You'll also note, unfortunately, I still have heat transfer, so this is a Fourier law which reduces the problem. So now I have K, whoops, and if K is a constant, I don't have to worry about this particular overbar, but K is just your heat conduction constant. Some things I want to note is I've neglected second coefficient of viscosity. And why? Well, the stress term, lambda, second coefficient of partial u, partial x, I, is on the order of delta squared, my boundary layer thickness. And that's small compared to the other stress terms. And in compressible flows, this would go away anyway, but I'm still looking at compressible flows. You'll note that delta is assumed to be small, so the volume might be, the atmosphere, my boundary layer thickness might be a centimeter or less quite easily, even if it's a really thick boundary layer. Higher speed flows, thinner boundary layers, higher turbulence. So if something goes on the order of delta squared, it's easy to remove it in this analysis. This isn't what Prandtl did at all. He actually was formulating it based on incompressible Navier-Stokes equations, but I'm just trying to present it in a more general way. So I think what we're going to do, now that we formulated our general equations in 2 dimensions for turbulent boundary layers in XY coordinates, is take a break for 10 minutes, and we'll come back at 12:45 and look at the laminar flow assumptions. Okay? So thank you.